Great. So let's get started. So I'll give I would say a very introductory look into machine learning. This is really kind of, hopefully will set the stage for some of the talks we'll hear about later today and also tomorrow. And then my talk will be followed by Yushan's talk, which is also an intro to molecular dynamics. So hopefully those two intro talks will prepare you for the rest of the presentations, where different speakers will go into a lot of detail in their respective projects. And so really the first question is, what is machine learning, right? So this is actually a definition that was made in 1959, if you can believe this. This has been around for a long time. And it's a field of study, or it's a set of methods that gives computers the ability to learn without being explicitly programmed. And I've added the from data piece. This is actually, what a lot of people now add to this definition. So what does this really mean? And so here's like a comparison of how we used to do things and how we do things now with machine learning. So before, you would have some level of knowledge about the problem, right? You would have some data, and you would actually write the program. So you would write how you want to take that data and interpret what the solution is or what the output is. With machine learning, this actually is flipped on its head. So you present the data and the output to a computer, and it comes up with a program. So it comes up with the representation of the relationship between the data and the output. It's a very different way of looking at things. And so I want to, again, point to this date, 1959. Why did it take so long, right? So here's a brief history of machine learning. And really the first time that machine learning and AI was talked about was in the late 1950s, right? In 1965, somebody actually made the first chatbot, Eliza. This was a computer that you could converse with, and it almost seemed like there was a human on the other side. This was a huge, huge milestone for machine learning. And then along the way, there's many innovations, right? So there is Deep Blue, 1997, that beat Garry Kasparov. So this was application to chess. If you go to 2002, Roomba, right? This is like the first, kind of true commercial product that we could hold in our hands that was based on AI and machine learning. And then in 2009, you have self-driving cars, right? The first self-driving cars. Also around that time is when Netflix started using AI for recommendations, product recommendations. So you have recommendation engines. 2011, you have IBM Watson that beat somebody in Jeopardy, right? And then we enter the age of like personal assistants, Siri, all of that. And now, today I would say machine learning is ubiquitous, right? It's pretty much taught in a lot of universities to people that are in computer science and even in other fields as well. And so there were a lot of technical innovations that had to happen along the way. One is we moved from traditional machine learning and, that looked a lot like statistics, right? And we've moved to deep learning, then into generative methods, and then reinforcement learning, right? So we've kind of made progress technically in terms of machine learning. But the other big kind of change that happened is the availability of data. This actually shows you the data curve from like 2010 to now and then projected. And what you see is that people actually don't even show the size of the data before 2010 because there wasn't much to talk about. And so a lot of the deep learning based innovations that are, where large data sets are really needed, they really started happening around this time frame, the early 2010s. The other huge kind of innovation was in hardware acceleration. And so with the use of GPUs for deep learning, in around 2011, that really kind of changed how quickly we can build models and leverage these large data sets. The last thing that I want to point out is none of this would have been possible, wasn't it for communities of people, developers, that basically build frameworks that have democratized machine learning for the masses, right? And so the first one in Python that was, super famous was scikit-learn for traditional machine learning. And then TensorFlow around 2015 came out for deep learning. And initially it was very difficult to use, was very painful. Now with TensorFlow 2.0, it's so much easier to do deep learning. But this is really kind of the progress, the historical progress of the field. So I want to talk about this for a second because, to everybody who's a hammer, everything looks like a nail to somebody who has a hammer, right? But there's situations where it's very useful to use machine learning, but there's also situations where you shouldn't use machine learning because it's really not needed. So when is machine learning useful? Well, there's several situations, and I try to group them into buckets. So one is when autonomy is required. So on Mars, you cannot drive a rover, right? You're too far away, and also you need something that's autonomous, right? But autonomy can also be desired in self-driving cars. I would love to have a self-driving car that I can completely rely on and just chill out. There's also a situation where, believe it or not, human expertise cannot be explained. If you try to explain to somebody, how do you recognize the speech or what I'm saying right now? It's actually extremely difficult. Or how do you recognize a cat or a dog in an image? It's very difficult to explain human expertise in some of these areas. And so this is where machine learning is very useful. Another place where it's useful is where you can benefit from automation. You may not always like that a lot of these products and services that you use are automated, but it does drive down their cost. And so fraud detection, for example, on your credit cards is all automated using AI. Various chatbots that sometimes you can't even recognize anymore if it's a person or not. And then also a lot of product recommendations, right? This is all AI driven. There's also places where there's potential to replace monotony, right? And really the typical example is helping mail, US mail recognize handwritten digits, right? Or words that people write on the mail. And so this is one place where AI really helped to recognize handwritten language. But another place that a lot of people don't realize is that AI is now almost ubiquitously used for histopathology. And so this is an image of like cells. These are cervical cells. And pathologists used to spend many hours and days looking at these images. These are very large images that you have to scan under a microscope very carefully to make sure that you don't find any cancerous cells or abnormal cells. Now you have AI systems that can essentially remove that monotony, where you only highlight to the pathologist the areas where there may be a problem, right? So 99% of this image can be scanned with an AI and just say, okay, everything is normal, and help the pathologist just look at what really you need his expertise to make a decision on. There's also situations, and we've seen this really great examples in COVID, where there's potential to gain time. And the big example that I really want to point out is drug repurposing, especially with COVID. So you can take existing drugs that have already been approved or have known safety profiles, and if you understand the way those drugs interact with our human receptors, and if you also understand how COVID interacts with those human receptors, you can very quickly find molecules that are effective as inhibitors, right, for blocking COVID from entering the cells or replicating. And so there's great examples in the literature of how this was utilized, how AI was utilized here. Another example is where you have to personalize a solution to an individual, right? So it would be very difficult to take the genome of a patient and write a program for every single person on how that genome, for example, should be utilized to personalize a treatment. But with AI, you can take thousands of genomes and really kind of do this in such a way that you build a model that now a new patient comes in and you can very easily predict the personalized solution for that person. And the last situation I want to point out is there's a lot of times when the data sets are too complex and too large for our human comprehension, even though we would like to pretend looking at the list of genes, from a gene expression profiling, that we really understand what's going on. I believe that in those situations, it's better to just start with machine learning, build the models, and then really use those models to point out potential mechanisms, and then you try to understand a little bit deeper. So when is machine learning not needed? Really anything that is deterministic. So for example, you really don't need machine learning to calculate your tax return or run payroll, right? And there's lots of situations where there's deterministic solutions that there's really no need to go to the machine learning space. But I'm happy to, when after we finish the presentation, I'm happy to kind of talk about the pros and cons of some of these solutions, right? Situations where sometimes you can get into trouble. So what are the key ingredients for machine learning? So the first most important thing is you have to identify the problem or task at hand, right? Before you say, I want to apply machine learning to this, ask yourself what it is that you're trying to solve, right? What is the kind of the solution that you're trying to build? And then after you have that, there's really three pieces. So you need data, so you need the source of data. You need to apply an algorithm, and there's many different solutions now for that. And the last one, this is also really important. You need to define what success looks like, right? Because this is what's going to be used to optimize the algorithm. Without the definition of success, you're not going to be able to build a model and to actually improve it. So to kind of make this a little bit more concrete, I'm going to use an example of a project that we worked on at Caliber, right? So there was a research team that was developing a novel therapeutic for IBD. And they only expected the population of the patients to respond. This is very common, right? Only some of the patients will respond to a drug. And the mechanism of the response was not completely understood. They had some thoughts about maybe what types of genes would be involved and what receptors, but it was really a bit of a black box. And so they wanted to develop like a predictive test or a companion diagnostic that could identify which of these patients would benefit from the therapy, right? And so at the start of the clinical trial, they were able to collect tissue biopsies from the large intestine to generate essentially transcriptome profiles, right? So from each patient, they had, gene expression on 40,000 plus genes. And at the end of this clinical trial, I believe this was like 12 weeks, they were able to collect responses, right? So histological responses in terms of how well did the colon cells heal, right? So they were able to see like a reduction in inflammation by visually inspecting the tissue. But they also could see other kind of metrics of IBD, very common metrics in terms of like how people, I don't want to give too many details this early in the morning, but how often do you go to the bathroom when you've got IBD as one of the endpoint responses, right? For making sure that a person is actually getting better. And so the data really is the gene expression for the 40,000+ genes, and the response is, can be a binary response. Did that person get better after the treatment or not? And so then what you do is you try to link you try to build a relationship between the changes in these genes in the patients, right? And whether they responded or not to the treatment. There's many different algorithms that you can apply to this type of problem. For those of you that have some familiarity with machine learning, logistic regression with some regularization that gives you the feature selection is actually one of really great solution for this type of situation. The reason why logistic regression is a good idea actually is because it is linear. So when you get your weights for your genes at the end of the day, it's interpretable. So you can say if that gene goes up or if it's elevated, it's related directly to the response, or it's inversely related to the response. So that's one thing that I just want to point out if you want to kind of dig deeper into this. And the last thing is the definition of success. And so the definition of success here was the ability to identify responding patients with greater than 80% sensitivity. So that was part one of the definition of success. And this is something that you can, quantify from the model. I'll go over this in a little bit. And the second part of the definition of success is using less than 30 biomarkers. In the clinic or later when you develop a test, you're not going to do a transcriptome profile. It's just too expensive still. So you need to do like a small assay, which means you need a small number of biomarkers to kind of really build a model. And so the final result was a model that relied on a handful of genes and was able to identify responding patients with a pretty high level of sensitivity. So this is like a real example of actually applying, machine learning on a project to help. in like a real life situation. So now that I've given you this concrete example, I want to go over how do we develop a machine learning model. And we're going to use this slide a few times in the talk, and we're going to talk about each of these steps in a little bit more detail. So first, you need a source of data. So you need to kind of think about which databases are available, what data do you have at hand, where can you collect data that really kind of helps you train the machine learning models, where there's examples of, of basically, in that case was transcriptome profiles and responses, right? So it doesn't just have to be the data that you generate. There can be other sources of data and databases that people have published. The next step, and this can actually take about 80% of the time on the project, is cleaning the data. And so this is really, kind of making sure that the data that you have is, sometimes you have to do some quality control. You have to decide which sources you're going to trust, which sources you're not going to trust. As you know, in biology, a lot of people use different assays under different conditions to get results. And so this step can be actually very painful and very long, depending on where that data comes from. The next step, and this is really important, is you need to find a way to represent the data numerically to a machine learning algorithm. And so a word in a sentence, that's not numerical. A peptide is not numerical. Neither is an image, right, when you look at it. So this is actually a really important step, and I'll go into detail on exactly, what we need to do to represent something numerically. The next step is splitting the data. And this is very important, and this is where machine learning and statistics, I would say, diverge in terms of their practical way of approaching problems. So statistics generally takes the entire data set, it builds a model, it gets you p-values that you can decide if things are significant or not. In machine learning, we do something really simple. We basically take the data, we split it into trained data and test data, and we hold out this test data until the model is finished, so to speak, so then we can evaluate how well it does. And this is really very similar to like a kid going to school and the teacher teaching certain material, right? This is the training material. And the teacher would generally never really show the quiz questions to the students before the test, right? You wouldn't teach the quiz questions. This is exactly what's happening here, is we're holding out some information as test data to evaluate how well the model is doing. And on the training data itself, we actually split that data as well. And if people have questions about this, I can go into this. But the training data also gets split into multiple pieces while we train the model, because we also need a little bit of data that we always hold out to score the machine learning model. And this is generally referred to as cross-validation. And we can talk more about that later. So once you have the training data, you apply an algorithm to that data to build a relationship between the input and the output. This gives you a machine learning model, and then you can take that model and you can score it. So you have some sort of a metric, whether it's accuracy or some other metric that you decide, that helps you figure out how well this model is doing, so you can make adjustments. These adjustments can be a change of algorithm, a change of parameters in that algorithm. Sometimes you actually need to go back to this step where you decide that you need to generate additional features, or you need to change the representation. So occasionally we have to loop back into this feature generation step while we're training these models. So once you have the model trained, then you take the test data and you predict it through that model. And then what you have is, on the test data, you know what the actual results were, right? You know what the answers were. So you can compare the actual to the predicted values, and then you can evaluate how that model is doing on basically data it has never seen. And we'll talk about some of the different things you can do. And the last step is really kind of deploying this model into situations that you want to use it for. So predicting new data, allowing others to predict new data. So this is kind of like the final step where you actually have a model in production. So I'll go into more detail into each of these steps. So the first step is this idea of representation, right? So how do we represent, data as features to a machine learning model? And I'll use a really simple example that we're all familiar with. And so you can take a house, right? And you can essentially break down a house into its features, right? So you can say that house is a certain number of square feet, has so many bedrooms, number of floors, it's the zip code, right, where it's located, whether it's close to schools or not. And what you're trying to do here is you're trying to predict the prices of houses that haven't sold yet, right? And you're using historical data of houses that have sold previously to try to build a relationship between the house that's on the market and the price that it's going to sell at, right? So here we're really taking the house and we're breaking it down into different features that can be represented numerically. Like each of these is actually, a numerical representation of what a house is. And so then you have these features, right? And then you're trying to predict a price of a house that hasn't sold yet. Really, the goal of the algorithm is to just come up with these weights. I know this is an oversimplified way of looking at things, but really the algorithm just comes up with the weights for these features that you have built in, right? So the human builds the features, the algorithm comes up with the weights. It's actually, pretty simple. But there's other things that don't look like a house. They're not so easy to break down into features, right? And so this is an image. I know this is very pixelated, but here's an image, right? So as a human being, this is what you see. Now, as a computer, if you actually represent this, image to a computer, right? The computer actually sees just a matrix of numbers from 0 to 255 if it's black and white. And so the lower numbers you can see here are darker and the lighter numbers are higher, right? So closer to 255. And so this is how you actually feed in an image to a machine learning algorithm, is as this n by m matrix of numbers from 0 to 255. If you have a color image, this is just 3 different channels, right? So there's RGB channels and each one is from 0 to 255. So you literally are feeding this matrix of numbers. And in this example, it was like names of famous people to the machine learning algorithm to teach it how to effectively recognize this set of pixels as a person, right? It almost seems magical, right? And if you look a little bit deeper into how this happens, and so what you do is you create this, deep neural network that has multiple layers, and the layers are all interconnected together. And at the lowest layer, you feed this set of pixel values, right? This image, which are essentially numbers, right, from 0 to 255. And then you feed it names of, famous people associated with those images. And what you notice is that the different layers of the network, the networks actually learn how to recognize more complex features, right? So initially, it's just edges and gradients of color. Eventually, it's literally parts of faces and then combinations of those features that allow the algorithm to learn how to recognize famous people. The advantage of using this type of data representation, so in this case, we didn't build any features, right? We just presented the data as is, as a set of pixel values. The advantage is that you don't make any assumptions, right? So you allow the deep learning based networks to learn the features that are needed to solve the problem, right? In fact, looking at what features are created can kind of help you understand how do algorithms actually solve some of these problems. The other advantage is that typically these types of approaches, these are called deep learning based approaches, are generally higher performance. And unfortunately, there's always a trade-off, and the trade-off in this case is that it has larger data set requirements, right? So you need to feed, a lot of data into these deep learning based networks to kind of get the higher performance. And this is what's shown here is so when you have very small data sets, traditional machine learning, which is kind of what we talked about, where we break down a problem into a set of features, they actually perform better when you have small data sets. But as you get larger data, these deep learning-based networks, especially the large neural networks, they essentially leapfrog the performance of the traditional machine learning models when the data sets get bigger. So this is kind of the typical trajectory, I would say. So if you have very small data sets, I would say start with traditional machine learning. If you have extremely large data sets, go ahead and throw it into a deep learning based network. And so the next step that we're going to go into, just want to remind myself of what's coming up, is the algorithm, right? And this is kind of my favorite part, because a lot of people see machine learning as this like magic, right? Somehow this algorithm magically like comes up with this solution, but it's actually not magic. It's actually relatively straightforward. And so I just want to take you through an algorithm that is behind most of the machine learning based systems and just try to hopefully explain how it works. And so like we said, the goal of the algorithm is to come up with these weights, right? These weights that help you build a relationship between features and the outcome. And what we can do is we can, because we have the actual and the predicted values, we can estimate error on a problem, right? And so we can say, that in a certain situation with certain weights that we've found, we have X error, right? And we can represent this error as this kind of smooth curve, which is called loss curve, right? So this is kind of how we try to represent error in machine learning, as this kind of smooth curve, right? And the reason why this is important is that we can use this curve to actually find ideal weights for being able to predict this outcome, right? So how is this best weight determined? So I just want to take you through how this happens step by step. So let's say that our initial value of our weight was right here. So this was our starting point. We randomly initialized the weights, and the weight just happened to be in this position. So what we can do is, because we've built this loss curve to be this kind of smooth kind of system, we can take a derivative at this point, right? The sign of this derivative tells you which side of the curve you're on, right? So if you're on this side of the curve, you would have a derivative that's negative, right? And the slope of this derivative tells you how far of a step you should take to get closer to the bottom of this well. And so at each iteration, you're really kind of taking your weight and you're walking it closer to the bottom of this well. So literally what you do is you say my new weight is my old weight minus a learning rate, which is really kind of tells you how big of a step you generally want to take, times the derivative of at this loss curve. So there's an actual equation that you're following every time you update a set of weights. And in multidimensional space, this is known as gradient descent. This is kind of like the workhorse of machine learning. This is kind of the magic behind how we come up with these ideal kind of solutions. And I'm happy to go into more detail if some people didn't quite, understand it. As Wendy said, it's 4:30 in the morning for me. So I hope I'm explaining this properly, but I'm happy to kind of go into more detail on this again after we're done. So then the next thing that I want to kind of briefly touch upon is how do we score a machine learning model, right? So after we found those ideal weights, how can we actually quantify how well the model is doing? And so we have this held out data, right? So we have the test data that we held out from the algorithm, right? And then we know the actual values. So we know the truth, and we're trying to compare the truth to the predicted values. And in a situation where we have a binary solution, where we're trying to literally predict like a 1 versus 0, right? So present, not present, disease, no disease. We can express, we can compare basically the predicted to the actual values using what's called confusion matrices. Don't ask me who came up with that name, right? Confusion matrices. And this is basically what you can represent the actual and the predicted values as, right? So if your predicted value is a 1 and your actual value is a 1, you have true positives. If your predicted value is a 0 and the actual value is a 0, you have true negatives, right? And then you have your false positives and your false negatives, right? And so, for example, if you build 4 different models, which are represented by these 4 confusion matrices, just by looking at them, you can very quickly tell which is the best model, really. So you want a lot of true negatives and a lot of true positives. So you want it to have a lot of values on this diagonal, and as few mistakes as possible on the off diagonal, right? So this is in machine learning how we quantify model performance. But also, once you have these confusion matrices, you can calculate all sorts of metrics. So you can calculate accuracy, sensitivity, specificity based on these formulas. And then there's situations where you may want, for example, more specificity versus more sensitivity, right? Depending on the problem at hand. So you can actually decide which of these models you're going to use moving forward that gives you, the performance that you prefer. And with this, you can also say, exactly how well your model performs. So if somebody asks you, how accurate is your model, right? You can actually give them a number and show how you derived the performance of that model. Of course, the key here is to have test data that represents real world performance. And sometimes the test data that you will have at hand is maybe not going to be completely representative of what happens in real life. And so that's why sometimes you can overestimate performance. And so once you've kind of developed the model and used your test data that's available to evaluate performance, you always want to later go back once that model is deployed and say, how well is it performing 6 months from now or a year from now that the data has changed? And so the last thing I want to show you is just a few different ways of interpreting of what's happening with the models, just to help you kind of understand that, building a machine learning model is not just for the purpose of having a machine learning model that has great performance, but you want to learn about, how does the model work, or why is the model making the predictions that it does? And I'll go into more detail on this tomorrow when I give the talk on the peptides. But for example, with peptides, we can represent a peptide sequence as a set of physiochemical features, right? So for example, we can represent charge or solvent accessibility or hydrophobicity of a peptide and build a machine learning model. This was actually a model for antimicrobial peptides. And then we can look at the weights, right, of the features in that model. And so features that have really high weights would have, more relationship to, in this case, antimicrobial peptide activity. So here, what we can see is that charge and solvent accessibility were kind of the key drivers of a peptide being antimicrobial or not. And so this is one way that you can look back at the model and say, how is it performing, and what are kind of the key features that it decided that are important in this case for predicting antimicrobial peptides. Now, the other thing that you can do, and this is actually something that I prefer to do, is to take examples of positives and negatives and just plot them in what I call these spiderweb plots, right? So for example, we can take peptides that had the highest predictions for being antimicrobial peptides, and we can actually express the frequency of different amino acids in that peptide, and we can see that the antimicrobial peptides are actually all kind of having the same pattern, right? So, quite a large frequency of neutral amino acids, acyclic, the charged acids are going to be right here, right? Yeah, so basically very kind of similar pattern for the top predicted peptides. But then when you take negative peptides, right, and you plot them, they have all sorts of different patterns, right? And so you can see how a machine learning algorithm would be able to recognize this type of peptide pattern and find antimicrobial peptides versus kind of filtering out all the non-antimicrobial peptides. So this is one way that I just kind of like to visualize what's happening with the models. And the last thing I want to show you is we can take a model and now deploy it into real life situations. And I'll talk about this tomorrow, but we can take models and predict novel peptides that have specific properties, such as antimicrobial activity or other activities. But then what we can also do, which is really powerful, we can take those models and we can predict all the substitutions, right? So this is, again, an example from antimicrobial peptides. We have a peptide sequence at each position. We have already an amino acid that occurs. We can predict all the substitutions, right, through the model. And in red, we have predictions that increase in activity. And in blue, we have the predictions that decrease activity. So very quickly, you can take a peptide and you can get a global view of what is happening if you were to substitute that peptide at each position. You can see that in some positions, if you mutate, you get basically a decrease in activity no matter what. So you see a lot of blues at a position. And in some cases, you can quickly see certain substitutions that would give an increase in activity. And then you can take this and you can go out and test this in the wet lab, right? And this is exactly what we did. And so there's a lot of things that you can do with machine learning. And I don't know, it just really the sky's the limit. It's really limit of your imagination of what you can use a model for. And so the last thing that I want to end here because a lot of people ask this question. How is machine learning different from statistics, or what is really AI, right? What is AI? And so with statistics, really the way it's really not that different. So early machine learning was really based on statistical models. It was really not that different from statistics, right? So both uncover patterns in data, right? So we're trying to build a relationship between input and output. A lot of them share common algorithms, right? But statistics, like I said, it puts more emphasis on p-values, right? And using those to help you determine if something is significant or not. Generally, you throw an entire data set into a statistical model, versus with machine learning, really the focus is more on predictive performance and scalability. And we apply this method of splitting the data into train and test set to evaluate performance rather than worrying about p-values and whether something is statistically significant or not. So that's really, I would say, kind of the key difference. But then what is AI, right? So AI, with AI, a lot of the times, and this is not defined, right? Everybody has their own definition. It's really about building more autonomous systems. Usually it's collections of machine learning models. And the other kind of feature that differentiates AI from machine learning is it's generally less specialized and more general, right? And so, when you're moving away from like just having a model, for example, that predicts an antimicrobial peptide to having a model that can, I don't know, let's say predict a novel peptide for some new virus that hasn't emerged yet, that's really kind of moving from machine learning to moving towards AI. But the last thing I want to tell you is, 5 years ago, I went to a conference, a data science conference, and somebody made this comment. I don't remember which company it was, but they basically said, oh, if it's in code, it's machine learning. If it's in PowerPoint, it's AI, right? This was kind of like the joke 5 years ago, but I don't think this is a joke anymore, because right now we have AI systems that are able to do things that really makes your hair stand. And one example is, I don't know if you guys are familiar with DALL-E, but DALL-E is a program that you type in a sentence. In this case, it was like bears mixing chemicals or mixing colorful chemicals. And DALL-E comes up with an actual image of your language representation of what you've conjured in your mind, right? So I highly recommend that you go and play with DALL-E. You have to sign up. It takes a few days to get the email access to DALL-E, but it's really incredible, right? So imagine you take a sentence, right? And you translate that into a piece of art. I mean, that's no longer machine learning. That's definitely AI.